Sample problem. A positive electric charge Q is distributed uniformly along a line of length 2a lying along the axis between y equals -a and y equals a as shown in the figure. Find the electric field at point P on the x-axis at a distance x from the origin. Here we take a small segment dq of the rod and determine the electric field at point P by the segment. We see that the distance r is just the Pythagorean equation, and we notice that as we evaluate the charged rod the distance r changes. Examining the equation for r, we see that the distance x along the horizontal remains and only the y distance changes. Here we divide the rod into infinitesimal segment ds as shown here. This small segment has a small charge we call as dq and it exerts a field on a point P. Now if we have another segment that is identical to the previous one but positioned on the opposite side, we have a cancellation of the electric field along the y-axis. So we see that the net electric field is solely due to the x-axis. We write the net electric field as A. We consider now the integral function, which we write now as equation 7. We modify this function to incorporate the parameters of a charged rod as shown in equation B. Expanding further the integral, and we now left with the function with r distance as shown in equation C. The cosine function can be calculated by examining the figure as shown here in equation D. Substituting this back to the equation, we have function A. We note that dq is a representative of the rod, so we consider the linear charge density function as shown by equation F. The linear charge density is evaluated on the total length of the arc 0 to 2 pi a. So equation E can be written as equation G. So we can also factor out the linear charge density and we arrive at the solution for the net electric field at point P as shown by the equation here. We substitute the linear density as shown here, and finally we need to solve the integral factor in equation H. Note we retain the constant x, which we will use later in solving the integration. So we isolate the integral function of equation H. We let y as a function of tangent theta, and this in turn turns dy to a function of x times the squared secant theta. So we continue to manipulate the function further and we arrive at a much simplified function of the integral as a function of secant as shown in equation I. So let us examine the solution of the integral or equation I and substitute back the parameters. Comparing the figure, we see that the sine function is given as a ratio of y over the length r. Substituting back the functions, we get a modified equation I. We then evaluate this integral from a to -a and we have the solution for the integral shown in equation J. We then substitute this back to the equation of the net electric field in equation H. Substituting back to equation H the solution of integral equation J, we arrive at the solution to the net electric field exerted by the charged rod onto a point P away from the rod shown by equation K.